Here are a few more examples on finding a possible formula for a rational function given the graph or certain information. So again, the rational function has to be polynomial divided by another polynomial, and a lot of the information from the graph pertains to the actual equation. For example, any zeros of the graph will be the same thing as zeros in the numerator of our rational function. So if we create this function, for this particular graph, the only x-intercept is at 2. So this value here is a 2. So on the top will just be x minus 2. Remember, you put it in the factor, you change the sign. So there's the numerator. If you remember, the denominator gets set by any vertical asymptotes that are on the graph. So looking at this one that we're given, we have vertical asymptote at -1 and +1. So in the denominator, we'll have x plus 1, x minus 1, changing the sign for each of those. The other thing that has to be satisfied, there is a y-intercept up at 2, and there also appears to be a horizontal asymptote here on the x-axis at y equals 0. So even though there's no indication y equals 0 is a horizontal asymptote, you can see the end behavior of the function here approaching the x-axis, so that would clearly indicate that there is a horizontal asymptote of y equals 0. And for a rational function, that happens when the degree of the numerator is less than the degree of the denominator. And currently, we have that in check. So we don't really have to do anything else to this function. The only other additional thing you could do if you wanted to is sometimes there's this constant value times the polynomial function. And for the one that we have, if we plug in the y-intercept, which it does give us, the y-intercept here at 2, if we plug that in, 2 in for the y value, 0 in for all the x's, you'll get -2 over -1, which is 2. And that'll show you that the constant is just a 1. So really, there's nothing to put in the front. And the function for this graph that's possible is x minus 2 over x plus 1 times x minus 1. All right, here's another one. So you're creating a rational function. So we can start with the zeros if you like. There are zeros or x-intercepts at -2 and +3. So the top factored pieces will be x plus 2, x minus 3. Then you have the denominator, which are going to give you vertical asymptotes. So that's for the denominator. So we have vertical asymptotes at -1 and +2. So our factors will become x plus 1 and x minus 2. All right. Then the only other thing, there's two things actually. You're given a horizontal asymptote at y equals 1. And if you have a horizontal asymptote and it's not 0, then that means that the degree of the denominator was the same as the degree of the numerator. And when you pull those coefficients, in this case they're going to be x squared, then it was just 1x squared over 1x squared, so you get the horizontal asymptote at 1. So there's nothing really to add in terms of a constant value for that part. The other thing that you could check if you wanted to is this y-intercept that they give you at 0, 3. So if you make your y equals and then put a constant there and write down your zeros and your asymptotes in factored form, and plug in your point, 3 for the y value, 0 for all the x's, you can verify that your k value is going to be 1 again. So the top is -6, the bottom is -2. -6 divided by -2 is +3. So yeah, that constant out front here is just a 1, and you don't really write the 1. So the function for this equation is just the x plus 2 times x minus 3 over x plus 1 times x minus 2. There's nothing really else to add or multiply to the front of that. Okay. Here is another one. So for this one, again, look what you have. So it's create a rational function. The denominator will come from vertical asymptotes. There happen to be 2 of them. One's at -2, so I'll do x plus 2. The other's at +3, so I'll put x minus 3. So that sets our denominator. The numerator, if you remember, is where any zeros or x-intercepts are on the graph, and this particular graph only has 1 0 at the origin, which is an x value of 0. So the factored piece, or the term that you put up top, is just going to be a single x. There's no other points that you're given. There's no other. The only other visual thing that you can see here is the end behavior of the rational function as x goes to infinity, as x goes to negative infinity. It appears to have a horizontal asymptote at y equals 0. And if you recall from the different ways the numerator and denominator can compare, you get a horizontal asymptote of y equals 0 when the degree of the numerator is smaller than the degree of the denominator. And we have that, and the top is an x, and the bottom will have an x squared. So we have that relationship going on, so we're good. There's nothing else to add, or multiply rather. So the function that could represent this graph is x over x plus 2 times x minus 3. That's all there is for that one. Okay. So this last one is slightly different. Where was the other one? Oh, the first one that we looked at had it had a horizontal asymptote, but notice it crossed it and then started to approach 0 at the end, which is what long-term behavior does. It's at the end, and it's okay to cross horizontal asymptotes because it happens again in this one. There's a horizontal asymptote at 1. Even on the negative infinity side, horizontal asymptote at 1, but the graph crosses it and then comes back down to it here on the end. So for this one, if we look at what we have, visually there's only one vertical asymptote, which is going to be indicative of the denominator. So it's -2, so we'll do x plus 2 as a quantity. The top is where you put your zeros. So the only x-intercepts for this graph are at -3. So we'll do x plus 3. And then there's another one at 1. So we'll do x minus 1. All right. Again, going back to the horizontal asymptote. It is at y equals 1. And the fact that it's a non-zero horizontal asymptote means that the degree of the numerator has to be the same as the degree of the denominator, and when you pull off the coefficients from those leading terms, it needs to be 1. Currently, if you look at the powers, you have x squared on the top and a single x on the bottom. So the only way you're going to get the degrees to be equal is the bottom needs to have x squared. So the best and easiest way to do that is the only factor that's there, x plus 2, is to square it. So now, even though there's x plus 2 in the bottom, you still only get that one vertical asymptote, but now your power on the bottom is x squared, it's x squared on the top. You satisfy the condition to have that horizontal asymptote. It gives you a y-intercept of 3/4. So if you would like to check to see what if there's like a constant value out front, you can. Remember, you just do y equals a constant and then write your factored form and then plug in this case we had a y-intercept of 3/4. So you plug 3/4 in for y, 0 in for all the x's. And cleaning that up gives -3. Oh, -3/4. Sorry, it's a -3/4 y-intercept. -3/4 equals constant times -3 over +4. So you see that that coefficient is just a 1. So there's nothing really to multiply on the front of that. So the equation here is x plus 3 times x minus 1 over the quantity x plus 2 squared. And again, the squaring came from the fact we had this horizontal asymptote. We needed those degrees to be equal, and the only way we could do that was to give the denominator sort of like a double solution. It doesn't double the vertical asymptote, but it just doubles the fact that there's the x plus 2 appears twice.